In this class, we will discuss about an important concept called shear center. It is also called as center of friction. Actually, it is defined as a point through which, if the shear force acts, then the member is subjected to simple bending without twisting. So, actually, shear force we can call it as resultant shear force. That means in any structure, if you take any cross section, if you apply the load in such a way that if the load passes through that shear center, then it will not be subjected to any twisting. It is subject to only bending, simple bending or pure bending. So it is very important in the case of non-circular sections or thin-walled open sections. Because in the case of thin-walled open sections, the torsional strength will be very less. It is torsionally weak, like channels, angles, and T-sections. So torsionally it is very weak, or in other words, your GJ value, torsional rigidity value is very low in the case of thin-walled sections. So in such types of sections, if the load is allowed to pass through the shear center, then it will not be subjected to any twisting. So to avoid twisting, so we can have that concept. It's a very important concept when a thin-walled sections are subjected to torsion. So actually, if you want to speak about the location where that shear strength center lies, of course it depends on the type of section we are going to use. So it is like this: the shear center, which is normally denoted by S. So the shear center coincides with the centroid of the section. It coincides with G, centroid of the section. If the section is symmetrical about both the axes, so if the section is symmetrical about both x and y, or you can take it as z and y, then your centroid of the section coincides with the shear center of the section. For example, you take a symmetrical I section, or a section like this, or a hollow square or rectangle section. In such types of sections, since you can see that the sections are symmetrical about both the axes, your shear center and the centroid, they coincide. So you need not locate whatever centroid is there, so that itself is the shear center. On the other hand, if the section is symmetrical about one of the axes, let us say here I have taken a channel section where it is symmetrical about x axis. In such a case, shear center lies on the axis of symmetry. It lies on this axis. Of course, centroid also lies on the axis, but they need not coincide. That is the thing. So suppose if you locate the centroid of this channel section, it may come somewhere here. G may come somewhere here. But S will be somewhere here. But both of them, they are lying on the axis of symmetry. That is second one. Next, the third point is, if the section is made of two narrow rectangles, like this T section or L section like this or like this, then shear center lies on the junction of both rectangles. Junction means if you draw the center lines like this, they intersect here. The center lines intersect here, so this is called as a junction. So here the shear center lies, and centroid lies somewhere here along this. So here also, this is the center line of this rectangle, this is center line of this rectangle. So point of intersection is this. So shear center is this one, and centroid, you know that centroid lies on the axis of symmetry, which is this y-axis here. Similarly here, as this intersection of these two center lines is here, so this represents the shear center, and centroid is here along the axis of symmetry. So these are the 3 points you have to keep it in mind for in the case of location of shear center. It depends on the type of section. So if it is symmetrical about both the axes, centroid and shear center, they coincide. If it is symmetrical about one of the axes, shear center as well as the centroid lies on the axis of symmetry, but they need not coincide. And if it consists of two rectangles, then the shear center is nothing but the intersection of the center lines of the two rectangles. So, just already told, thin-walled sections, it is very important to locate the shear center. In the next lecture, I am going to explain with an example how to locate the shear center, numerical example I have taken. So, in the case of solid sections and not the hollow sections, Closed hollow sections means it can be like this. So it can be hollow circular section, or it can be hollow rectangular or square section like this. So if it is like this, then normally these are very strong in torsion. That means torsional rigidity value is very high. That we have studied in your strength of materials. So in that case, if the load is then another important property is that the centroid and the shear center, they are very close to each other in such types of sections. So in that case, if you apply the load passing through the shear center, then the effect of torsion can be disregarded. So it can be omitted. So these are the two important points you have to note down. That is why the location of shear center is very, very important when a section is subjected to torsion. And we will define one important term called shear flow, that is F. So shear flow is nothing but variation of shear stress. You can take variation of shear stress per unit length. That is called as the shear flow, and its unit is Newton per millimeter. It is given like this. So it is called as longitudinal shear flow F. It is given by SA y bar by I, where S is the shear force acting in that longitudinal direction, and AY bar is called as the moment of area under consideration about the neutral axis. Very, very important. Neutral axis, you know that the stress at the neutral axis level is 0. So that is taken as the reference. So we have to note down the area about the neutral axis, and we have to note take the distance of the centroid of that area from the neutral axis, and you have to multiply that by the area above the neutral axis. So you are going to get this AY bar term. So this of course we have used in strength of materials for calculating the shear stresses in beam cross sections. And I is the moment of inertia of the section about the neutral axis. Maybe IXX or IZZ you may have to take. So the units of these shear force is normally expressed in newtons. AY bar is expressed in millimeter cube because A is in millimeter square, Y bar is the distance in millimeter, I is the moment of inertia in millimeter power 4. So if you see the unit of this F, it will be S is in Newton, AY bar is in millimeter cube, I value is in millimeter power 4. If you simplify that, you will get in Newton per millimeter. That is nothing but the shear force per, you can take it as shear force per unit length. Shear force per unit length. So Newton per millimeter. So that is the unit of shear flow. Now if you take a simple example of a channel section which is symmetrical of course about the z axis here. I have taken horizontal as z, vertical as y here. So centroid lies here, shear center lies here. So the distance of the shear center from the center line of this web portion, I have taken it as small e, or you can call it as eccentricity. E because it is eccentricity. And here these are the dimensions. B is the width of the flange, PW is thickness of web, TF is thickness of flange, and H is the distance from the center line of the top flange to the center line of the bottommost flange. So your centroid lies here, and the shear center will be this side. Anyway, both of them they will lie on the axis of symmetry, which is Z here. Now, if you show the shear stress distribution for this section, if F is the shear flow in the flange and F1 is the shear flow in the flange, F2 is the shear flow in the web, assuming the direction of shear flow like this, when this is subjected to torsion, shear stress is a resultant of the torsional effect. So if you plot the shear stress variation, it will be 0 here, it has some value tau 1 here at this edge, and here the value at this edge for the web portion, tau 2, and tau max will be somewhere here at the neutral axis. So this is the neutral axis. So you have studied in bending stress and shear stress that bending stress is 0 in a flexural member at the neutral axis level, where shear stress is maximum at the neutral axis level. So now here, since it is symmetrical, whatever total is there this side, total also will be there this side, and these two are symmetrical, therefore tau 1 to 0, it will be like this. So here, F1 is the shear flow, F1 and F2 is shear flow, tau 1, tau 2 are the shear stresses. So now, later on we will see how we can compute these shear stresses and how we can locate this eccentricity, that is distance of the shear center from a particular reference point. So the concept of shear center is very, very important in the case of mainly thin walled open sections as well as in closed hollow sections of solids when they are subject to torsion, because the torsional effect to omit, to disregard the torsional effect, we have to locate the shear center, and as far as possible we have to apply the load. We have to apply the load. We have to analyze in such a way that the load has to be applied through the shear center. Then we can easily neglect the torsional effect. The member is subjected to only pure bending or simple bending without torsion.